Hello friends, in the previous few lectures we have been considering different approximation techniques. Now if you can recollect, this approximation technique, the foundation on which we built to arrive at this approximation technique was we considered a metallurgical behavior or a materials behavior that we often observe during a phase transformation. This behavior, which we refer to as the nucleation, it acted as our foundation stone on which we built our understanding, and wherein now we are at the point of discussing the different approximation techniques that are used to solve a given derivative. Now, when you revisit what we looked into or what is the formulation that we adopted to discuss the nucleation was, we consider that the nucleation rate of the given system is proportional to the number of nuclei that is present in the system. So therefore this yielded us such a linear relation, and since this relation is rather straightforward, we were able to solve it analytically, and we were able to arrive at a toy model that would help us determine what would be the number of nuclei that we can expect in a system at a point t. And this expression we were able to derive it as something like this. And this we were able to do it analytically, and we also solved it using some approximation techniques. And since we have already handled it analytically, we were able to cross verify the outcomes. Now, even for this a simplistic case like this, where the derivative of the function, the derivative that we need to handle is of a linear nature, even for such a case, when you want to identify what is the number of nuclei, when you want to have a meaningful sense out of the expression that comes out of by solving this derivative, when you want to use the solution for this derivative, we need to have two additional parameters. So this derivative of this expression here yields as a solution, and when you want to use the solution meaningfully, we need to have information about two additional parameters. One is the initial condition that is here, the other is the constant of proportionality. Only when we have these two parameters, we will be able to make sense out of, or we will be able to make use of this function here, which again talks about what is the number of nuclei that is present in a system at a given time t. Now, when your derivative or this expression here is simple or rather straightforward, linear in nature, we were able to do both analytical and approximation. Now, often this expression would be convoluted. Then in that case, what we would adapt is we would use this approximation in a computational framework. Now, what essentially we would do is we would adapt this approximation using, or we will use this approximation and feed it to a computing machine, and then try to arrive at or try to solve this derivative here. Now, before going any further, I just wanted to give you an idea how this particular approach of using approximation in a computing device to solve complex derivative works. That is, I would like to spend some minutes on rather elucidating what happens when you use a computing device. How does this approximation works within the framework of a computing device? When you involve a computing device, how this approximation works. Now, we have considered several different approximations. One of the approximation is the forward difference. Now, when you use this forward difference key, generally, in general case, is expressed as that the derivative of a function f of x can be estimated by x plus delta x minus f of x by delta x. So, when you have a function f of x, and forward difference means you are considering a point beyond x forward to x, and then that will give you x plus delta x and minus x, and with respect to its original point. So you are able to solve or approximate the derivative using the scheme here. Now, in this case, in case of the nucleation rate, what essentially this expression is all about is the nucleation rate. What we are considering is the time difference. What we are considering is how the nucleation is happening, how the number of nuclei is increasing as the time progresses. And for that case, even for the linear case such as this, we saw we need two important parameters to solve or to make sense out of the solution of this derivative here. One is the initial condition, and other is the constant of proportionality. What it means is that this expression here should be of some relevance. This expression here should be actually our starting point. This should be some relevance, and we should know what this constant of proportionality is. So only when these two parameters are known, we will be able to handle the solution of this simple derivative, this linear derivative. Now the same goes for the other complex derivative, and the same goes for when we are solving complex derivatives using in a computation framework or using a computation device. So we need an initial condition, and we need to make, or we need to handle this expression in the initial stage, in the initial case. So at time x naught, we should be able to solve this expression. We should be able to solve for this derivative here at the initial condition. So we need two parameters. One is the initial condition, and second is constant of proportionality. What we mean by constant of proportionality is that when you substitute, when you consider this nucleation rate at x naught at t0, then it will be kx naught. So it means this is known and this is known. So therefore the nucleation rate at t0 is known. For a simplistic or a linear ODE, we need these two in order to solve this derivative and in order to make sense out of this derivative. So the same goes for solving complex derivative using a computation device. Now again, we want to see the relevance of this approximation within the framework of a computational device. Now correspondingly, when you rewrite this forward difference scheme for solving the nucleation rate, it would be d of x of t by dt. It would be something like x of t plus 1, or rather so x of t plus 1 minus, or rather x of t delta t and x of t divided by delta t. So this is rather, let me rewrite it in a more legible way. So this is x plus delta t minus x of t divided by delta t. So what essentially we have considered is this expression. What we have considered is nuclei, number of nuclei after at a time t. So that would be this, the number of nuclei after the time delta t, and that would be this expression, and we divided by the time span width that we have considered, that is delta t here. Now we need to solve this expression, and we need to know what would be the nuclei at t plus, or number of nuclei as t plus delta t. So our model, when we say that when we are solving this particular derivative using a computational device, what essentially we are doing is we are attempting to estimate what would be the number of nuclei that is going to be present in the subsequent time step of t plus delta t. So that is essentially what we will be doing when you are solving this particular derivative in or using a computational device. We know what is the number of nuclei at a given time t, and we need to find out what will be the number of nuclei in the next step of t plus delta t. Now when you consider the initial time step, that is t0, that means x of t0 will be x naught. So this is the initial condition. Now at t0, we know what x of t is, that is x naught, and in the same way we should also know the derivative at t0, like we saw here at x naught. What is the derivative? Like in this case, we were able to estimate, for a simplistic case, we were able to estimate what is the nucleation rate at the initial condition. What is the nucleation rate at t0 is known. Now when both these are known, what can be done then subsequently is we can rearrange this expression in such a way that x, the number of nuclei at an unknown time t in the future, is nothing but the nucleation rate at the initial condition into the time step width plus the number of nuclei at the given time t, and since this is the initial condition, so it will be x naught. So how the computational, or how solving this derivative works in a computational framework is, it starts at time t0. It begins with time t0, and at time t0 there are two parameters that are known to us. One is the derivative and the other is the initial condition. Now this delta t is defined by us, so correspondingly what we will be able to do is we will be able to estimate what is the number of nuclei that will be present in the subsequent time step of t plus delta t. Now if you assume t plus delta t as time step 1, now it is possible for us now using this expression here, using this combination of terms here, we will be able to estimate what is the number of nuclei that is going to be present in the next time step of t1. So at t0 we have the initial condition, and now we have been able to find out what would be the number of nuclei that is going to be present at t1. Now using this, what we can subsequently do is we can subsequently estimate. So now that we know what is the number of nuclei that is present in the time step t1, we would be able to use the same approach and then estimate what would be the number of nuclei that would be present in time step t2, which would be t1 plus delta t. So we would be adopting the same technique, and then we will be estimating what would be the number of nuclei that would be present in the time step t2. So this one will help us understand what is the number of nuclei that is present at t1, and now what essentially we will be replacing is this will remain the same, and x0, the number of nuclei that is x0, will be replaced by x1, which is the number of nuclei that is present at time t1, which we have identified, which we have determined from this expression here. And we know the rate, we know the derivative, or we know the nucleation rate at t1, so correspondingly we will be able to estimate the number of nuclei at t2. So what essentially we do is we start off from the initial condition wherein we know the nucleation rate at x0 at the initial condition, and we also know the number of nuclei that is present in the system at t0, which is again the initial condition. We know the nucleation rate at the initial condition, and we also know what the initial condition is. When we know both these, what we will be able to do is we will be able to identify or determine what will be the number of nuclei in the next time step. In the future, what will be the number of nuclei. And once we are able to do that, once from t1 or t0 we are able to move to the next time step of t1, then at t1 now we know the same two conditions, that is the number of nuclei that is present in the system and the nucleation rate that is in that or at that time step. So again we now know these same two parameters, and the delta t is something that we defined. So correspondingly, now in this case we will be able to find out the number of nuclei that is going to be present at the time step t. So what essentially we are doing is using a computing system, using a computing device, what essentially we are doing is we are iteratively solving this relation over different time steps, and we are then subsequently replacing one time step, or we are consequently replacing these two. So these two parameters here, they get subsequently upgraded, so they get subsequently updated, and thereby we are able to rather predict, or rather we are able to develop, or we are able to show how the evolution of the number of nuclei is. So what essentially we are doing is we are just focusing on this one equation, and we are solving it iteratively by updating these two parameters here. So these two parameters, it will be x1, and this will be nucleation rate at time t1, and we will be updating it to t2 and the number of nuclei at t2. So when you keep on updating these, and when you keep on iteratively solving this, what we will end up having is we will be able to show that how the number of nuclei is increasing as the time increases. So this is how computationally the model that we have developed work. It starts off with an initial condition, and then by iteratively solving and updating the corresponding parameters. It's not just iteratively solving a given expression, but updating the corresponding parameters, we will be able to show how the number of nuclei varies with time. So we will be able to make sense out of this expression that we have already seen, how the number of nuclei varies with time. That means how the nucleation rate of this corresponding evolution is, we will be able to do that. So essentially, using a computation device, what we will be doing is, even using the simple forward difference scheme, we will consider a given expression and we will find out the number of nuclei that will be present in the future time step by subsequently updating, by progressively updating the new parameters. And this is this is what would be the base of the code often which you write in order to model the nucleation. When you want to model the nucleation, when you consider the framework of this code, what that code essentially entails, this is what it would entail. You will have a single nucleation relation, that you will have a single expression that is often devised to predict what would be the number of nuclei in the future. And there will be updating terms that needs to be updated, and in this case these are the two terms that will be progressively updated, and this here is the simple constant. So when you consider any evolution equation, in this case is the evolution equation for the number of nuclei that is present in the system. Evolution meaning as the time proceeds, how the number of nuclei varies. If you consider any differential equation that is solved using a computing device, you could find such a framework associated with it. Now, having understood how a given derivative is handled using a computational device, particularly when that approach involves an approximation technique, let us move on to extend the applicability of this approximation techniques. So what essentially we have seen is, we have seen that when you have a function and when you have a relation that involves a derivative, an expression that involves a derivative, be it complex or straightforward, we can use an approximation function to solve it. You can use it to solve in a pen and paper, or you can use to solve it computationally. And when you use to solve it computationally, it involves an iterative process, and iteration, not only iteration, but the parameters that are involved get accordingly, correspondingly they get updated, and we will be able to then solve for the derivative, any complex derivative using a computational device. Now, the applicability of these approximation, they do not rather get restricted to the functions alone. So these approximations, they cannot handle only functions alone, but they can also be used to handle data sets. So what do I mean by that is, so whenever you consider the approximation, what we have been so far considering is a function of x. So this could be any complex function, and we have been considering the derivative of this functions or function of x. Now, the applicability of this approximation, the places wherein this approximation can be employed, it goes beyond the functions, it goes beyond this continuous function, but also it can be adapted to handle discrete points. It can be adapted to handle discrete points. So what I mean by a discrete point is, supposing you have a data set, and for a given input, so you are doing some studies, and that studies gives you or generates your data set, that is for a given input x1, you get an output y1, and this y1, since it is dependent of x1, can be expressed as function of x1, and you continue to do this experiment and you generate such a data. So yeah, a generalized one will be x of I, which is a function of x of I, and you are intended with. So we have considered, you have fed in n inputs, and for n inputs you are able to receive. So you have performed this experiment separately, and for each time you varied your input, and you are able to arrive at a different output each time, and you have proceeded, or you have conducted this experiment n times, and you are able to arrive at n outputs. Now, this set of data involving the input and output, the derivative of such data, the nature of such a data can also be estimated using these approximation functions that we have considered so far. Now, when you want to find the nature of this data, how the derivative of this data is, we can use these approximation techniques to understand or to evaluate the derivative of these data points that we have. Now, when you consider the different approximation that we have seen, one that we have seen is the forward difference, and that is written as this, and the other is the backward difference, which is written in this manner. And finally, we have seen the center difference, So we have seen the central difference, and all these rather can be employed to estimate the derivative of a given function. Now, when you consider these different approaches, we saw that the errors associated with each of these approaches are different. So in case of the forward and difference, or the forward and backward, the errors are rather of the order of delta x. In case of the central difference, the errors are in the order of delta x square. So it means when the delta x tends to 0, it is not exactly 0 when the delta x tends to 0, what essentially we have is the error associated with the central difference is an order less than the error associated with the forward and backward. So this is forward, backward, this is forward difference, backward difference, and this is central difference. So the error associated with the central difference is the order less than the forward and backward difference. Now, the same approach can be used to handle the data sets. Instead of the function, the same approach can be used to handle the data set, and the conventional way of writing the forward difference when it handles the data set. So when we handle a data set, the way of writing it would be, if this is the generalized representation of the data set we have, we feed in xi and the output we get is f of xi, then the forward difference will adopt a form of this sort: f of xi plus 1 minus f of xi divided by delta x. Now, in case of a given function, it is rather possible for us to choose the delta x in such a way that the delta x is rather equally spaced. So in this case, when we consider 2 points, that is x plus delta x and x minus delta x, particularly in case of central difference, it is possible for us to choose, when we are handling this function, it is possible for us to choose the delta x in such a way that this delta x is equally spaced between the 2 points that we have considered. We have a function, we are selecting a point, and it is possible for us to consider 2 additional points which are equally spaced with respect to the central point. However, we cannot expect the same out of the data set. The input that you feed, of course, will depend on, it is possible for us to feed the input in such a way that the difference between the input are maintained to be constant in between the different input variables, but this cannot be ensured because we have to deal with the machines, the input often is dependent on the machine that we are handling, and because of this condition, we might have to vary the difference between these input. It might not be the case that the difference, that is x2 minus x1 and the x3 minus x2 might not be equal. So it means it is not possible for us, particularly in a actual situation, to ensure that the delta x between the different input variables are constant. So in those cases, the way of representing how the derivative of a data set such as this is identified or estimated using forward difference is, all we need to consider in that case would be the difference between the inputs. In the denominator, all we need to do is consider the difference between the inputs. So the first key point is, it is possible for us to use this approximation techniques to find the derivative of not only function but the data set that involves output and input variable and the output set of inputs and the output variables. Now, it is not necessary that the spacing between the input variables needs to be identical. Even if they are not identical, we can directly use the input variables themselves in the denominator, and we will be able to find out the derivative using the forward difference scheme. So this is the approach that we, or this is the expression that we adopt when we want to identify or estimate the derivative of the data set such as this. Now it is possible for us to express the similar relation using, or similar expression using the backward difference scheme. All we need to do is replace x plus 1, or rather x of I plus 1 to x of I minus 1. So when you do that, we will be able to express the backward different approximation of the first derivative. And in the same way, we can also express the approximation, or the way, rather, should be x. Yeah, it is also possible for us to express the central difference scheme for identifying the derivative or for this data set. So now, when you consider this data set here, exclusively the one that is written here, and if you are given a choice of finding the derivative of this data set here, a smart choice would be often to adapt the central difference scheme. Now we have seen that for how the expression of the forward difference, backward difference and central difference approximation would vary for the data set. All we need to consider is I, and this I is one of the data set, and for forward difference you need to consider the next data set, and backward difference the previous data set, and for central difference you need to consider, so I plus 1 is the next data set, I minus 1 is the previous data set. And when you know these next and the previous data set, when you know the the data point that is next and previous to the given data point is known, we will be able to use the central difference to estimate the derivative of this function. Again, the spacing between these data points need not be identical. Even though they are different, we will be able to rather use the central difference to find its or central backward forward to find its derivative of this data set. Now, when you are given such a data set and you want to find the derivative of this data set, and you want to ensure that the derivative is as accurate as possible, then the reasonable choice would be to use central difference scheme, because this accuracy of the central difference scheme is an order greater than the forward difference and the backward difference. So therefore one would easily one would prefer using the central difference scheme in order to estimate the derivative associated with this data set here. However, there is a problem associated with using the central difference scheme for this data set. That problem is usually or is observed when you focus on the first data set here and the last data set here. When you consider the data point x1 and xn, so x1 is the first data set and the xn is the last final the end data set, the terminal data set. When you consider the terminal data point, when you consider these 2 points, it is rather not straightforward for us to use central difference scheme. In this case, we don't have any point above or preceding this data point here. Preceding x1, we don't have any data point, and subsequent or after succeeding this x1, xn, we don't have any further data point. So therefore, using central difference scheme for the first and the last data point is practically not possible. So therefore, one cannot adopt the central difference scheme for all the data points to estimate the derivative. In that case, what we need to do is, in case of x1, then we are forced to use the forward difference scheme. In case of xn, we are forced to use the backward difference scheme. So when we are handling a set of data, and in this case, while handling the set of data, and while particularly when we want to find the derivative of it, even though we are able to find the derivative using central difference for most of the data points, the first and the last data point, they pose a problem. In case of the first data point, we can only use forward difference. In case of the last data point, we can only use the backward difference. Now, if this was the case while we are doing a simulation, while we are handling or doing a simulation, what you can do is, when we are setting up a domain, when we are setting up a system and we are considering the initial and the final point, we can introduce appropriate boundary conditions so that it is possible for us to handle the data at the data x1 and xn. So the first data and the last data. So in order to ensure that we are solving the first data and the last data, derivative of the first data and the last data using central difference, we can consider, or we can set up an imaginary x0 and an imaginary x plus 1 as boundary conditions and solve x1 and xn using central difference scheme. So when what we are dealing with is not a data set but a domain. When you are considering a domain, when you are considering a system, and we want to have a finite system, and when you consider a finite system, it needs to have some boundaries, and using central difference scheme the boundaries will not be possible. So what we can do is, we can impose a boundary condition to use the same scheme with which we are using at the central regions, at the other regions along the boundaries as well. So that is where the boundary condition comes into play. However, the same condition cannot be adapted for the data sets, because data set is they are the actual point, and we cannot adopt such assumptions for the data sets. So in those cases, we are forced to use forward difference on the backward difference. Now, if you can think about it, what is wrong with using forward difference and backward difference? The error associated with all these other points will be an order less than the error associated with these first and the last point. So what we will have is, we will have an inconsistent errors associated with the derivatives that we identify using the approximation technique. Now what essentially we are trying to do is we are trying to handle a data set, and we have first and the last data set. We cannot use central difference. Had it been a system, had it been a finite system, we could have used an imaginary data points for and beyond the final and the starting point, and then we would refer to that as the boundary condition, and we would have used the same approximation. However, this being a quantitative data set, we cannot do the same. But the only option that in that case what we can do is use the forward difference or backward difference. The problem with using forward difference or the backward difference is this accuracy associated with the forward difference and the backward difference will be an order less than the accuracy associated with all the rest of these terms. So what essentially we are introducing is an inconsistency. Now in that case, our solution, our way out would be ensuring that the forward difference gives us an order, forward or backward difference, both. It gives us an order of error that is similar to that of the central difference, that is delta x square. So when we are able to arrive at an expression or arrive at an approximation scheme that would give us the order of an error that is similar to that of the central difference, then we have solved this problem. Then we will have an accurate description of the derivative associated with this function. So all the derivative associated with the data set rather would be of the order of delta x square. If we are able to identify a scheme that identify as forward difference scheme or a backward difference scheme that is of the order of delta x square, then we will be able to ensure that all the errors of this data points, all the errors associated with these data points are of the order of delta x square. Now in order to do so, let us revisit our expression for the forward difference, that is f of x plus delta x minus f of x delta x. This is what? This is how we have considered the forward difference thus far. Now one possibility for us in this case is, while we don't have any backward or any point above the x1, we have, in addition to x2, we also have points that go far beyond the x2, meaning we have after x1 we have x2, and after x2 we also have x3, meaning there are points that go, and even though we don't have any points above x1, we have points that go beyond x1. So therefore let us try to make use of the points that go beyond x1. So just what it means is that instead of considering just x plus delta x, it is possible for us now to consider x plus 2 delta x, because there is a data point that is associated with x plus 2 delta x. This data point would be, in this case, f of x3, and this point would be f of x2, and this is f of x1. So what essentially now we are doing is, instead of focusing on just the immediate point alone, we are now focusing on the point after the immediate one. So we are considering 2 points forward from our desired point. So instead of considering just x plus delta x, what we are considering is, we are considering rather in addition to the x plus delta x, we are considering a point that is beyond the x plus delta x, that is point x3. So even though initially the forward difference only involves x1 and x2, now we are including the point x3. So this x3 is of the form x plus 2 delta x. Now similar to how we were able to determine the error associated with the forward difference scheme, let us try to Taylor expand each of these individual terms. So when you consider this f of x plus delta x, which is nothing but the f of 2, this can be written as f of x plus f prime of x. Again, this f prime of x is nothing but the f of x plus dx delta x, and f double prime of x, second derivative of f of x delta x square by 2 factorial, f triple prime of x delta x cube by 3 factorial, and so on and so forth. Now when you consider the other forward point, the forward point two, that is 2 steps beyond the initial point, that would be f of 2 delta x. Then this can be written as f of x plus f prime of x 2 delta x, f double prime of x 4 delta x square by 2 plus f triple prime of x 8 delta x cube by 6. What I have done is I have just expanded this 3 factorial and so on and so forth, and we written it in this manner. Now let us try to arrive at an expression wherein we don't have any denominators for this Taylor expansion. So it would be 2 f prime of x delta x plus 2 f double prime of x delta x square plus this would be 4 by 3 f triple prime of x delta x cube. So all that we have done is we have just simplified these fractions here, and we have arrived at this expression here. Now we have an expansion for f of x plus delta x, we have an expansion for x plus 2 delta x. Now when we want to arrive an expression for, when we want to approximate this f prime of x, the first derivative of f of x, and the error associated with it should be of the order of delta x square, then what we essentially need to do is we essentially need to focus the error. We need to have an error associated with this term and above. The dominant error should be associated with this term here, because this is something, this approach is something that we have looked in our previous lecture. What essentially we will be doing is we will be handling, or we will be summing up, or we will be relating these two terms here, x plus delta x and x plus 2 delta x, and we will be trying to arrive at an expression for f prime of x. And when we arrive at an expression for x prime of x, often what we would do is we would bring this f of x to this side, and we will bring the delta x to the bottom, and when we bring the delta x to the denominator, the other term, the subsequent term on which the error would depend on would be this term here. The error would largely then depend on this term here, and then the error depends on this term here, and when you have removed delta x out of it, then correspondingly the error would be dependent on delta x. So essentially our general approach would involve moving this f of x to the left hand side of your expression and taking the delta x common and then dividing it. When we do that, when we take the conventional approach, then our error would depend on, the dominant error term would be this term, and the error would be dependent on delta x. This is what we have seen in the previous lecture. If we want to get rid of that, and if we want to arrive at an expression wherein the error is dependent on delta x square, then the errors then should be, the dominant error term should be this one. So essentially what it means is that we need to manipulate these two expressions, that is these two expressions, we need to manipulate it in such a way that we are able to get rid of these terms. So when we are able to get rid of these terms, that is this term, the term associated with delta x square, if we are able to get rid of this term, then the dominant error term would be the subsequent term. So this terms would be the dominant error terms, and that means we would be able to arrive at a forward difference scheme wherein the error associated with it is in the order of delta x square. So when we are able to get rid of this term, then the dominant error term will be this one, and the error associated with the in the order of delta x square, which is similar to that of the central difference. So it is possible for us to have a forward difference scheme with an error that is equal to the error associated with the central difference. Now when we want to get rid of this term here, what essentially then we have to do is we have to multiply this whole of this expression with 4. So when you multiply this whole of this expression with 4, that is when you have 4 f of x plus delta x, when you do that, then the corresponding expression would be 4 f of x plus 4 f of, or f prime of x delta x plus 4 f double prime of x delta x by 2 factorial plus 4 f triple prime of x delta x cube by 3 factorial, which is 6, and so on and so forth. Now this we can write it as 4 f of x plus 4 f prime of x delta x plus this to get cancelled out, so 2 f double prime of x delta x square, and this term would be 2 by 3 f triple prime of x delta x cube, so on and so forth. So we have 4 x plus delta x, and we have f of x plus 2 delta x. We have 4 f of x plus delta x and f of x plus delta x. Now let us consider f of, or rather 4 f of x plus delta x minus f of x plus 2 delta x. When we consider that expression, when we subtract this 1 and 2, so this is nothing but 1 minus 2, 1 minus 2. When we do that, what we would end up having is 3 f of x, and when you consider these two expressions here, that is 4 f prime of x and 2 f prime of delta x, then it would be 2 f dash x or f prime x delta x, and then these two terms get cancelled out like we desired. These two terms gets cancelled out, and finally what we would end up having is these two terms here and here will get cancelled out, and the third term then would be 2 by 3 minus 4 by 3 f triple prime of x delta x cube. So we have considered f of x plus 2 delta x, and we have considered f of x plus delta x. For the f of x plus delta x, we have multiplied it by 4. The reason we have considered 4, because we have to get rid of a specific term in order to ensure that our order of error is rather similar to that of the order of error associated with central difference. So that's the reason we multiplied 4 to the f of x plus delta x. Now we are separating 4 into f of x plus delta x minus f of x plus 2 delta x. When we do that, we end up with an expression something of this sort here. And now we can replace all these terms here, and when we do that, what we would end up having is 4 f of x plus delta x minus f of x plus delta x minus 3 f of x. This would be, then we can take the delta x out. This then would yield, so when you take 2 delta x out, this then would yield f prime of x minus, this would be minus 2 by 3. So this, if you consider what is the difference, it will be 2 by 3 minus 2 by 3, and we have taken 2x, so it will be 2 by 6, so 1 by 3 f triple prime of x. So of course these are solutions that, or these are simplifications that we can try out for yourself. But what essentially then we have is, when you bring this downwards, then when you rearrange this, what essentially we have is x plus delta x minus f of x plus 2 delta x minus 3 f of x 2 delta x would be this expression. The whole of this expression would be d of f of x by dx plus an order, so this would be square, plus an error of order delta x square. So when we perform all these different numerical operations, when we do this over this when we rearrange all these terms, what we finally end up having is the order of error associated with this forward difference is the one similar to that of the error that is associated with the central difference. So both forward difference and central difference now have the error of the order of delta x square. So therefore essentially what can be done is, we can now consistently adapt the forward difference to handle the data point, the initial data point or the first data point, and the same treatment can be adapted for the a backward difference, meaning when you consider f of x minus delta x f of x minus 2 delta x and f of x, we would be able to arrive at, using these combinations of these terms here, using the combinations of these three data points, we will be able to arrive at, or we will be able to estimate the derivatives which have the order of the central difference, which have the order that is similar to that of the central difference. So when we have set of data points, and when it is difficult for us to use the forward difference or the central difference for the initial and the final data point, all that we need to do is we need to consider an additional point in the scheme that is possible to us. So in case of the initial point, the scheme that is possible to us is the forward difference. So therefore, instead of considering the immediate point alone, if we consider two immediate points, we will be able to estimate the derivative using forward difference, which has an accuracy similar to that of the central difference. Now when you come to the last point, the final point of xn, instead of considering the immediate immediate backward point, if you consider two immediate points, that is f of xn minus 1 and f of xn minus 1, instead of considering just xn minus 1, if you consider xn minus 1 and xn minus 2, then you are considering two immediate points, and when you consider two immediate points and use backward difference scheme, you will be able to arrive at an expression, a scheme that has the error that is equivalent or identical to the error associated with the central difference scheme. So therefore, there is a unique difficulty associated with while handling data points, particularly when using approximations to find the derivative of the set of data points, and this data points or this difficulty can be solved by increasing the data points that we consider in the forward or the backward difference scheme. When we increase the data points that we consider in the forward or the backward difference scheme, we are essentially improving the accuracy associated with the backward and the forward difference scheme, and we are able to arrive at a scheme, we are able to arrive at an approximation that is equally accurate like that of the central difference scheme. In the next lecture, we will see why it is relevant for us to identify or estimate the derivative of a given set of points. Now, of course, there are set of points and there are numerous things that we could do with this set of points. Now, in the next lecture, we will see a practical significance of identifying the derivative or estimating the derivative of a given set of points. Goodbye.